Hello everyone, welcome to this lesson. So in this lesson we're going to go through Euler's method Python code. So if I recap briefly, we have discussed that solving ordinary differential equation involves two different parts. The first one is an equation describing a relationship between a derivative and the original function, which in this case dy dx is equal to 2y, and also we have an initial condition. At x equals 0, y is equal to 1, and we're going to be using those two pieces of information coupled with this Euler's method, which in essence is a linear extrapolation, to get an estimate of this exact solution, y is equal to e to the 2x. And we have found out three different step sizes, 0.5, 0.2, and 0.1. And we got an estimate of this e to the 2x. And we saw a pattern that the smaller the step size, the more accurate the solution, as you can see from the 0.1, which is the gray here, is because it actually minimizes the effect of the curvature of the function on the technique, since this is actually in essence a linear extrapolation. So the code in this lesson is actually a very, very simple code, and you can actually see it from the size here, because we are merely taking this one line of code, which is the Euler's method, and we're applying it for different points here. When we dealt with 0.5, we were getting an estimate of 0.5 and 0.1, and we essentially applied this at 0.5 to get an estimate, and then took the information at 0.5 and applied it at 1. So let's actually see how this would work in terms of the code. So the main equation that we're working with here is, of course, the differential equation, and we're going to define it as dy is equal to lambda x comma y colon 2 multiplied by y. Now, a comment on lambda expressions: when you're dealing with lambda that involves the dependent variable as well, you do have to define the independent and the dependent variable here, despite the fact that we don't have an x here. In coming lessons, we're going to see that sometimes a derivative is defined in both the independent and dependent variable. But regardless, you need to put x and y here, or this function will not work. So let's actually go into the initialization. Now, the initialization, the main purpose of it, of course, we want to add the initial condition, x is equal to 0 and y is equal to 1. So basically, we add this initial condition. But also, I need to calculate n. So what is n? N is the number of calculations that we're going to be performing, and that depends entirely on the interval that you're interested in. In this case, we're interested in 0 to 1, and also the step size. So when we were dealing with a step size of, say, 0.5, we did two calculations, right? We took the information at the initial condition to calculate the estimate at 0.5, then the information at 0.5 to calculate the estimate at 1. So we did two calculations, one at 0.5 and one at 1. So which means n is defined as the upper limit 1 minus the lower limit 0 divided by the step size 0.5. So 1 divided by 0.5 will give us n equal 2, which means we're going to be looping twice here to get the two calculations needed. So what if I do h is equal to 0.2? Well, 1 divided by 0.2 is going to give us n is equal to 5, which basically is a calculation of 0.2, 0.4, 0.6, 0.8, and 1. So the calculation of n here in our initialization stage defines how many times is the Euler's method loop going to loop to actually get us the estimates that we're interested in. So this is a very simple display code. So the first part here, print x \t y. So this creates the header. So when we're going to be creating these three tables. And also this one basically prints the first initial value here. So we have the %f, which is the placeholder for this first value here, x, %f, the second one, placeholder for the second value here, which is y. So we should predict that we get x and y, and we get 0 and 1. So let's actually go to the main code here. So this is a for loop. So for I in range 1 to n plus 1. So if you remember with the range, the last element is not included. So this in essence is 1 to n. And for 0.5, n is 2. So 1 to 2. So we're going to loop twice. So the first loop, the the second y is equal to the y that we have right now, which is 1 plus, and we're going to be calling the dy function, and we're going to be putting the 1 here, so 2 multiplied by 1, so 2 multiplied by 0.5, so this is going to give us the next y is equal to 2, and then we get the corresponding x, so x is equal to x here now is 0, plus the step size, which is 0.5, so 0 plus 0.5 is 0.5, and now I'm going to print my next point, which is basically 0.5 and 2. We go to the last loop, at least when we're dealing with 0.5. We have y now is 2, so 2 plus, and we go to the derivative 2 plus 2. 2 multiplied by 2, so that's 4. 4 multiplied by half, that's 2. So now we have 2 plus 2, that will give us 4. And then we get the calculation for the corresponding x, which is going to be x is equal to 0.5 plus 0.5, which is 1. And now we output 1 and 4. So let's actually see this. Okay, so here we have printed the header, we have printed the initial values 0 and 1, and with the 2 loops that we have gone through here, we did the 0.5 and 2 and the 1 and 4. So let's examine another step size. So 0.2, you can see, okay, so 1.4, 1.96, 2.744, and so on, which is basically identical to what we got here. So let's actually go through the last example. So 0.1. And okay, so we have 1.2, 1.44, 1.72, basically the values that we got here. You can see that we have from the second row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 different calculations, which is basically the, because n was equal to 10, and this looped 10 times to calculate everything after this initial condition. So before the second part of the lesson that I want to go through is, so we have basically developed the code, we have created these 3 tables. Let's actually go create this, this graph here. So for this graph, I'm going to be importing a few packages. So what I'm going to be doing here is I'm going to import the math, because I want to be defining the analytical solution. So I'm going to say f is equal to lambda x, and I'm going to call the exponential function, and I'm going to be defining 2 multiplied by x. So when I'm dealing with plots, you're going to be creating lists. So let's actually create the first list, which is, let's create x plot. So this is the x values, and I'm going to create an empty list for that. And I'm going to create a y, I'm going to call it y underscore Euler, and this is the second list. And also let's create a third list for analytical, so we can compare how well our estimation is. So then I'm going to add another line of code here, which is basically going to be appending all the x and y values that we're going to be generating. So it's going to make sense in just a little bit. So xplot, we're going to use the method append, and I'm going to append the x. Then I'm going to do the same thing for the Euler. This is dot append, and I'm going to put in the y, and this is y analytical dot append, and this I'm going to use the function for the analytical. So at this point, if you can see here, we have created this list, and this list. So the first thing that we're going to do when I go into the loop, I'm going to append the value that I have in x, which is 0. We're going to append the value I have in y Euler, which is y, and we're going to append the value we get from the function by evaluating that particular x, which is 0, which also is going to give us 1. So then we're going to go through all the loops, and you're going to see that for the last loop, generating y and generating x, but I'm not appending, which means this line of code, we want it one more time outside to capture the x and y value for the last loop. So now I actually have the lists for all the values that I want. So let's actually import the Matplotlib .pyplot as plt. So now I have imported a package to create a plot, and it's very simple. It's going to be plt.plot, and I'm going to be defining the x and y values. So xplot, then we have versus y Euler. So this is the first one. Then the second one, I want to do xplot versus y analytical. And let's run this. All right, perfect. So here we have, this is supposedly the analytical, and the blue is Euler. So for this reason, so you know you can distinguish each one of them, we can actually add a legend, and we're going to be passing a lists of the two values that we want. So here we have the first one that I defined here. You can see the x and y that I defined here is Euler, and the second one is the analytical. And if I pass this, you can see here I have the blue is the Euler and this is the analytical. We can also play with the formatting of these. So let's actually the first one, make it red with dark circles. So I can do R O here, and if I do this, let's add a comma here. All right, so I think this is much clearer. So here's the Euler estimation, and this is also the analytical. So let's actually try it for 0.5 for different values. So if I do 0.5, here's the analytical estimation. Here's the analytical solution, and here's the Euler estimation. If I do 0.2, we have this. If I do 0.1, you can see we have even a better estimation between 0 and 1. And we can even go to 0.05, see what we have here. So 0.05, you can see even the estimation is getting much, much better. We can even go further, say 0.01 for the step size, and you can see it's a lot of calculations, a lot of iterations, but nonetheless, we actually have captured both the trend and even the values for the for this function expansion 2x between 0 and 1. So let's actually do one more thing. Let me do this at 0.01. Let's actually add labels. So I can do plt.xLabel, and I can do x. If I run this, you can see I added an x label here, and also I can add a y label. Also plt.yLabel y. You can see I have y here, x here, and we have the analytical versus the Euler's estimation. So as you can see, actually it's a very, very simple code. Maybe the visualization code took just a little bit to write out, but it's also a very, very simple code. It involved creating 3 different lists, one for the x values, one for the Euler, and one for the analytical. We have created a line of code here to append the x, y, and also the function value. We have put it again here so it can capture the y and x for the last iteration. And also we have imported the matplotlib.pyplot as plt, and I was just merely calling the plot from this package and doing x versus y, and I have defined this as red, also with dark with solid circles, and also the x versus y for the analytical. And we added a legend, we added the x label and the y label. So you can see it's actually a very, very simple technique. In the next lessons, as I have mentioned before, we're going to be examining improvements on the Euler's method, because the inherent assumption that this is a linear extrapolation, you saw that actually we need to go to very, very small step sizes, like for instance 0.01, for us to converge to an exact solution, or a very, very close solution to the exact value. So that's it for this lesson, and I will see you in the next lesson.